So we want to look at some circuits that op amps are used in, and the first one that we'll look at is a very common circuit. It's an amplifier circuit. What it does is it takes an input voltage and it amplifies it for the output voltage. So it's, you can get an increase in voltage. So if we look here, you basically have an input voltage hooked up through a resistor to the inverting terminal. And then you have a feedback connection that goes from the output and comes back to the inverting terminal, and then the input of the non-inverting terminal is grounded. So assuming that this is an ideal amplifier, an ideal op amp, then the voltage difference between the non-inverting and the inverting is 0 volts, which means that the current into the inverting input is 0. So we basically, if we look, let me get this up into full screen mode so that I can make some annotations. If we look at this node right here, we have 3 branches that connect to that. We have the branch that's bringing in current I1, we have the branch with current I2, and then we have this branch going into the inverting input, which has a current of 0 amps because our amplifier is ideal. So if we were to express with respect to this voltage V1, current I1, it would be V sub I minus V1 over R1. That would have to be equal to this current, which is V1 minus V0 over RF. RF is, F is for feedback. A lot of textbooks will call this V sub I or R sub I for input. So you'll have feedback over input. This textbook just calls it R1, which is fine. All right, so here's that equation we just talked about looking at the circuit. And so we do have, if you recall, the voltage V1. So let's come back here and look at our figure again. This voltage V1 is connected here to this terminal. But remember, there's 0 volts between V1 and V2 because this is ideal and V2 is grounded. So V1 is going to equal 0, which means that in both of these expressions, V1 goes to 0. So we can get rid of that. And then we have VI over R1 is minus V out over RF. So that's what we have here. And you can rearrange that equation a little bit to get an expression for the output in terms of the input. And so this is the expression I want to look at. Okay, first of all, notice that the output voltage is negative whatever the input voltage is. So hence it is an inverting amplifier. So if you put 2 volts in, you're going to get negative some voltage out. The ratio between output and input is the feedback resistor to the input resistor. And this is referred to as the gain. Okay, and it's a closed loop gain because you have that connection that goes from the output back to the input, hence closing the loop or giving you some negative feedback. So the gain of this amplifier in magnitude is RF over RI. It does invert, giving you an inverse polarity at the output. You can adjust then the values of the feedback to the input resistor to give yourself the gain you want. And typically this is done to amplify the voltage. So, if you want to, you can have a gain. If you have a signal that comes in that is microvolts, you can have a gain of 10 to the 5th to give you tenths of volts coming at your output. Frequently this is done when you have very small signals, so very small voltages in a measurement, and you're trying to take those into, say, an oscilloscope or some other measuring device, and you would like to have a bigger voltage to measure and to work with. So a lot of times the very first stage of conditioning a signal or an analog signal or looking at measuring an analog voltage, the very first thing that's done is an inverting amplifier is used to give you this gain so that you're actually you're upping the voltage. Now, does this conserve power? Yes, it does, because obviously if you amplify the voltage, you're reducing the current. Okay, this is the equivalent circuit of the inverting amplifier. You notice it has, in this case, it does not have an infinite input resistance. The input resistance is R1. And so here you have the dependent source. It's shown with opposite polarity. The proportionality, the controlling variable is the input voltage. The constant is the ratio of feedback to input resistors. So this is how you amplify a signal. This is the equivalent circuit for that. And just as an aside, this is a way that you can make a current to voltage converter. Why would you do that? So if you had a current source, and people don't like to deal with current for a lot of reasons. So if you have a current source coming in, you take that through a resistor, that gives you a voltage VI, and then the op-amp will give you an output voltage so that you can deal with voltage instead of current. This is another example. This is how you would construct a non-inverting amplifier. We can analyze this in exactly the same way by applying KCL right here. The difference here is that this voltage V2 is not grounded. It's actually set equal to some input voltage. Now V1 minus V2 is still 0, but you do in this case have an input voltage. So you would write a KCL at this terminal, and if you simplify that, you find that you get two relationships. First, you get the relationship that we found here, which was applying a KCL equation to the inverting terminal, and then you can write a KCL equation or a node equation right here at the output terminal. If you do that, you get this relationship. Okay, so combining those two equations and eliminating some variables, you get this expression that puts your output in terms of your input. Now, after you've simplified the mathematics, you find out that you don't get this direct RF over R1, you get 1 plus RF over R1. So you don't get a negative sign, so this does not invert the input, but you don't get a direct ratio between feedback to input resistor. So it kind of, from a design perspective, if the gain is going to be very large, like let's say RF over RI is 1,000, then this 1 makes no difference at all. But let's say you wanted to make your gain equal to 1. You couldn't really do that with this circuit unless you let the feedback resistance go to 0 and ran a direct short back. So with a non-inverting amplifier, the disadvantage is your gain is always going to be greater than 1. Now, most of the time that's okay, and you want that because the reason you're building an amplifier in the first place is to get some gain. But there are certain circumstances where you would prefer not to have a gain greater than 1. You'd prefer it to be 1 or even less than 1. And in that case, you cannot use a non-inverting amplifier. Okay, so here is the example of what happens if you want to make a non-inverting amplifier with a gain of 1. You basically short out all of your resistors. So your feedback resistor is just fed to, your feedback line is just fed directly back into the inverting input. Feedback resistor goes to 0. Your other resistor R1 is also not there. You don't have that other resistor that comes into, go back, this resistor right here. It's also, it's opened. So this one is just, it's gone. It's removed. So this is opened. This is shorted. Hence, you've got nothing coming into the inverting terminal except the direct feedback line from the output terminal with no resistance. If you do this, the RF over R1 term or RF over RI term, depending on the book you're looking at, goes to 0 and your gain is 1. This is kind of a cool thing. It is called a voltage follower or a unity gain amplifier. Why would you do this? You would do this if for whatever reason you want to separate two circuits while still allowing a voltage signal to pass through. So why would you want to do that? Well, I can think of all kinds of reasons. You might want to do that because you don't want a lot of current flow. You want this input voltage to see an infinite impedance and then to carry that forward as the output. So this is it's a fairly common thing to do this. So you could basically you replace the feedback with a wire, you disconnect the ground, the gain would still be 1. So this is a voltage follower or unity gain. It'll produce an output that was equal to the input. Now this is kind of a cool circuit. This is called a summer. It's a way to add signals. So if you have 3 voltages and you want to get a circuit that creates the sum of these 3 voltages, you can do that with the following circuit. So you can see that you have each voltage input connected to a common node. In this example, the resistances are different, R1, R2, and R3. You can write a node equation here. And if you write that node equation, basically you can look at what these currents are and you can look at what this current is. And by writing a KCL equation and having all 3 input currents added together equal to the output current, you put those in terms of the voltages, and it turns out that by making a KCL equation there at that node, you end up with your output voltage being basically the sum of your 3 input voltages, each one modified by this ratio of R feedback over R1, R feedback over R2, R feedback over R3. So a lot of times all people want to do is sum signals. So they will make R feedback equal to R1 equal to R2 equal to R3, which means your output voltage is just the inverted sum of V1 plus V2 plus V3. And so that's kind of cool. And you don't have to limit your inputs to 3. You can have any number of inputs. So this just allows you to sum 3 things. So I told you this was kind of like an analog computer. This is a way to build an analog device that takes the sum of 3 signals. You can weight the sum if you wish. So if for whatever reason one of these voltages for your application should be given more weighting or priority, it can be multiplied by, you can do that by changing the value of R1 with respect to R2 and R3. Okay, a similar thing is the difference amplifier. In the difference amplifier, you have voltages V1 and V2. It is set up where V1 is like a inverting amplifier into the inverting input. V2 is a non-inverting amplifier into the non-inverting input. So it's like you took those 2 circuits, the inverting amplifier and the non-inverting amplifier, and you combined them using one op-amp. So one of those is going to be, this one is the inverting amplifier part, and so it's going to give you the negative sign because it's into the inverting terminal. This one is the non-inverting part, and it's going to have a positive sign. And if you make R2 much less than R1, this fractional thing here gets very small, and so you end up with a 1 for VA. I'm sorry. Let me go to the next page because we need to do another node equation here, and we need to get rid of VA. So this is writing it at node VA. So let me go to the next page, applying KCL at node V. Then when it's all said and done, here's what you actually end up with. You end up with this. So you've got R2 over R1 V2 minus R2 over R1 V1. And at this point, we won't go through a lengthy derivation of this, but I just want you to see for application purposes. So what you want is you want R1 much less than R2, and you want R3 much less than R4. If you do that, then this ratio is approximately 1, and you've basically built, if you then, have this R2 over R1, obviously if this one is small, this one's going to be large, but what you have is a difference multiplied by a constant. So a couple of things, this would be like building an analog computer subtractor, but the price that you have to pay in order to do the subtraction is this ratio R2 over R1 is going to be a large number. So it's not going to be a true subtraction, it's going to be a subtraction of two voltages multiplied by a constant. So that's kind of something that just goes with analog circuits that perform mathematical functions. Okay, and so here we go. Something called common mode rejection. So a difference amplifier rejects any signal that's common to the two inputs. Now this gets a little bit beyond the scope of this class, but basically if you set these two ratios equal, then you get this output that is the difference of these two times this factor R2 over R1. So what this means is if there's common signal between V1 and V2, in other words, let's suppose that you have a sine wave, and then superimposed on top of that sine wave, maybe you have a little peak for V1, and for V2, let's say you have your sine wave and you don't have a peak. So in this case, that sine wave, which oftentimes is background noise in the lab, it's common to both of the signals. And let's say all you really care about is detecting a peak. Then what you can do is you can build this difference amplifier, and what it does is it takes this signal and it takes this signal and it subtracts the two, taking out the common mode and giving you an output that's going to be only a function of whatever is different between the two signals. So that's a common thing done if you want to do a common mode rejection. Now one of the problems is that when you do that, you have a low input impedance because of that ratio between R2 and R1. So what people do is they trick the system by putting a non-inverting amplifier before the difference amplifier. So what that means is you can still maintain your infinite input impedance without, or your very large input impedance without, and yet still get a difference amplifier. So as I said, these last two circuits are a little bit beyond the scope of this course. It's just to show you, mostly so that you have a reference for when you take lab and you if you do try to build any analog devices. This is kind of an introduction to how to do it and how they basically work. I think that mostly concludes the well, this is just a useful statement. Instrumentation amplifiers are so useful that they're often packaged just as a single chip. And so instead of building this circuit out of all of these op amps and having to put this on a breadboard, you actually buy the entire circuit, and the only thing that you're changing is the resistor. The one application of this, in my lab, we measure biomedical signals. It's a really effective way at extracting a weak signal out of a large common mode signal. a classic thing for this is the signal that is obtained from muscle. So people who do things like research in prosthetics or research in trying to extract signals from, say, when a muscle is activated or a nerve is activated, you've got all this large signal present in your detectors from noise, movement, muscle engagement that's not relevant, and then you've got this little tiny signal that you're trying to pick up. So the hope is that the large signal is common to both probes, and then you can build this difference instrumentation amplifier that will take your difference and give you an amplified signal. So that's for what that's worth. One more comment about op amps, and once again, this becomes significantly more important in the lab and in circuits too. Because op amps have this infinite input impedance, we can do what is called cascading, meaning we can take the output of one op amp circuit and make it the input to another op amp circuit, and then we can take that output and make it the input to another op amp circuit. And basically each time the output voltage will be the gain times the input voltage. And so we could do this, multiple times with each of these amplifiers, referred to as a stage. And the reason you can do this is because the infinite input impedance of the amplifier to this output, this guy looks like an open and it doesn't load the circuit. So you can basically just do this any number of times. Now in practice, if you do this too many times, you are inviting instabilities and losses. So you got to be a little bit careful. Yes, theoretically you can do it an infinite number of times, but in practice it becomes pretty difficult because each op amp, to make it work in an optimum way, it's got to be tuned a little bit in the lab. So you do leave yourself open to a little bit of vulnerability if you try and stage too many op amps together in this way. Basically your gain gets too high, and so that can create some problems with things like frequency response and some other things. So if you don't remember anything else from this lecture, I would like for you to remember the inverting amplifier and the summer, because those are two important circuits. And I would like for you to remember the fact that you can build an instrumentation amplifier that will give you that will amplify the difference between two inputs. But really, it's really important for you to remember that you can stage or cascade op amp circuits like this. So you'll see this in circuits 2. You will most likely see it in some other classes as well. So just kind of the next time you hear about this, you will have seen it before, which was really my goal. So that concludes what I want to talk about with regard to op amps and cascaded op amps and op amp circuits, and hopefully you'll have seen them before when you go to your next